Every time you check a map on your phone, pull cash from an ATM, or watch a live news feed, you are relying on an invisible web of infrastructure floating hundreds of miles above your head. Modern society and modern militaries are entirely tethered to orbital satellites, but those networks share a fatal flaw. They are physically and digitally exposed. Hundreds of miles up, a critical communications or GPS satellite lacks armor or concealment, making it an easy target for cyber attacks, jamming, and kinetic weapons. If one of those critical assets goes dark, replacing it is not a quick fix. Historically, the aerospace industry requires a massive runway to get anything off the ground. Planning, building, and launching a replacement satellite typically takes anywhere from 3 to 6 months. In the context of global security, a 3 to 6 month delay is an eternity. During that blackout period, an adversary operates with a massive, uncontested advantage, moving forces and executing plans while the other side is effectively flying blind. Space is a brittle domain. When an asset is lost, the speed at which a nation can put a new one in the sky dictates the line between victory and defeat. To solve this massive vulnerability, the United States Space Force launched the Tactically Responsive Space Program, or TACRS. The premise of their latest test is extreme. The military orders a private commercial company to launch a fully functional replacement satellite into orbit and gives them absolutely zero prior warning. That test became a reality on June 19, 2026. At exactly 05:37 a.m. local time on the remote Mahia Peninsula of New Zealand, the official notice to launch is issued to Rocket Lab. The moment that order drops, the clock starts, on a sprint to completely rewrite the timeline of orbital access. By 6 a.m., just 23 minutes after the call, Rocket Lab activates its preparation sequence. They do this using a skeleton crew of fewer than 20 people. Operating with such a lean team requires clearing the usual hurdles in advance. They rely on heavily automated pre-launch checks and pre-coordinated airspace clearances with aviation authorities to slice through bureaucratic delays. By 12 p.m., the launch vehicle, the Electron rocket, begins fueling. The Electron is a lightweight, 18-meter-tall machine engineered from the ground up for rapid, on-demand deployment. This diagram shows the Electron's 3D-printed Rutherford engines, bypassing traditional manufacturing bottlenecks to build a complete engine in days. It also eliminates failure-prone turbopumps, relying instead on an electric propellant feed system powered by lithium polymer batteries, vastly simplifying design and enabling fast turnaround times. Rocket Lab didn't achieve this speed by rushing a standard launch sequence. They engineered the historical bottlenecks completely out of the hardware itself. At 09:30 p.m., the payload, a satellite named Pioneer, is successfully mated to the rocket. Built by True Anomaly, Pioneer is a highly agile inspection platform. Unlike static satellites, it carries advanced propulsion, allowing it to execute complex maneuvers, track moving targets, and perform dynamic engagements with other objects in space. Launching a highly maneuverable asset on such short notice proves a core military strategy: rapid restitution. This chart compares the timeline of an orbital attack. In the old system, destroying a U.S. satellite gave an enemy a clear 6-month window of strategic dominance. With rapid restitution, replacement satellites launch so fast that the enemy's advantage evaporates in under 24 hours. Extreme speed becomes the ultimate deterrent. An adversary is far less likely to spend millions attacking a space asset if they know their target will simply be replaced overnight. At 10:19 p.m., the Electron rocket ignites its engines and lifts off from the Mahia Peninsula into the night sky. From the moment the order was received to the second the rocket left the pad, exactly 16 hours and 42 minutes had passed. Rocket Lab shattered the previous world record by more than 10 hours. The efficiency continued once in orbit. Traditional satellites often need weeks of calibration, but the Pioneer satellite powered up and became fully operational just 38 hours after launch, beating its own deadline by more than a day. Looking at this chart of historical response times shows the scale of the achievement. In 2009, rapid launch meant 6 months of preparation. By 2011, it dropped to 29 days. In 2023, 27 hours. Now, in 2026, it is down to less than 17 hours. This single mission proves the space industry has left behind its slow, methodical planning cycles. Accessing orbit is now a real-time tactical operation. While Victus Haze was a military test, the mechanical and operational leaps required to pull it off will directly impact civilian space access. Consider disaster response. In the aftermath of a massive earthquake or a severe storm, specialized Earth imaging satellites could be deployed directly over the affected zone within 24 hours to precisely guide relief operations. Commercial telecommunications providers will use these exact same rapid launch capabilities to patch sudden global network outages, instantly flying replacement hardware to stabilize broadband for millions of users. Reaching orbit on demand pulls space into the immediate operational environment. It integrates the cosmos into a network of agile, democratized resources that directly support the resilience of the systems we use every day.